Hi everyone, welcome back to PLS 3100. We're getting very close to the end here. This is the second to last lecture with new content that you're going to get. Let's buckle up, settle down, and get done. In the previous lectures, we have covered all of the elements that make up the OLS. We have the push, the pull, and the direction. We talked about linearity and omitted variable bias. We also talked about how you need to do one hypothesis test per variable. To start our conversation for this video lecture, we must go back to the very beginning of the semester when we talked about variance. Variance was a measure of dispersion that gave us a sense of how far, on average, did the data fall away from the mean. We start this lecture with that idea, but we add a little bit more sophistication to it. Now, before we do anything, just remember that this is all for clarification. You're not going to have to calculate any variances. Imagine that the total variance of a data set can be broken down into two parts, the random part and the systematic part. Together, these two combine into the total variance. The random part is the variance we cannot explain, meaning there is some variation in the data set that we simply cannot explain. The systematic part is the variance that we can attribute to some systematic relationship. That is, the relationship between the dependent variable and the independent variable. This is often referred to as the covariance. What are the expectations that we can have about the error of an OLS? Well, a perfect OLS would be one that predicted every observation perfectly. That means the predicted value and the observed values would be absolutely identical. There would be no difference between them, and consequently, there would be no error. If there is no error, that means there is no random part of the variance, and the total variance would be entirely systematic. Or, in other words, the total variance would equal the covariance between the dependent variable and the independent variable. If we were to divide the systematic variance by the total variance, we would get 1. That is because any number divided by itself is always going to equal 1. Since the total variance equals the systematic variance, we have the same number divided by itself, getting us the number 1. If we were to graph that so-called perfect OLS, we would get something like this. The red dots represent the actual observations, and the blue line represents the OLS estimated values. The OLS line lands perfectly on top of the red dots, and therefore there is no error. Now imagine the opposite case, where we have a completely imperfect OLS. That means the OLS cannot estimate any values whatsoever. There is absolutely no systematic relationship between the dependent variable and the independent variable, and the variance is 100% random. Since there is no relationship between the dependent variable and the independent variable, there is effectively no covariance, or the amount of covariance is 0. If we were to do that division again, that is, if we divided the systematic variance by the total variance, this time around we would end up with 0, and that is because 0 divided by any number is always 0. When you divide 0 by the total variance, regardless of what the total variance is, you're always going to end up with 0. This process, where we divide the systematic variance by the total variance, is a sophisticated way for us to get some sense of the overall explanatory power of the OLS. This process, which consists of dividing the systematic variance by the total variance, produces a measure known as the adjusted R-squared. Its job is to inform us of how much of the variance can be attributed to the systematic relationship between the dependent variable and the independent variable. Let's take an example to clarify what we can do with this measure. Consider an OLS that produces a total amount of variance of 100. The systematic part of this variance, or the covariance between the dependent variable and independent variable, equals 70. Well, from that we can immediately find out what the remainder of that variance is. that is 30, and it's random. We get that because the total variance is 100 and the systematic part is 70. The total variance equals the systematic part plus the random part. So if the systematic part is 70 and the total is 100, then the random part must be 30, as 70 plus 30 equals 100. If we plug in those values into the adjusted R-square equation, we get 70 divided by 100, which gives you 0.7, or 70% explanatory power. In English, that means that 70% of the variation in the dependent variable can be systematically attributed to the independent variable, or x, our independent variable, accounts for 70% of the variation in y, our dependent variable. How is any of this useful to us? Well, to get that, we have to turn to an example. It has to do with variable selection. So take this as a start. You are interested in testing the claim that when it comes to conflict, countries are more likely to avoid conflict with each other if they trade more. You then find a data set that contains two variables. First variable is conflict, which is a score of how much conflict they have experienced. And a second variable is the number of trade treaties that have been signed between countries. Notice that off the bat, you can come up with an expectation of a negative or inverse relationship. The more you trade, the less conflict you will experience. So you do your due diligence and you check if this relationship fulfills all of the requirements of the OLS. It does, so you go ahead and you run an OLS. By the way, let's assume, for the sake of this example, that trade is the only variable related to conflict and there is no OVB here. I know that's unlikely, but we want to keep it simple. The OLS produces a beta coefficient of -2.2. The coefficient interval includes 0 and therefore you accept the null hypothesis. Basically, you conclude that there is no relationship between conflict and trade cooperation. It could be that the relationship between conflict and trade cooperation is just not real. Or it could simply be that the variable that you picked to represent trade is not a good variable. The OLS you ran used number of trade treaties signed between the two countries. Just because two countries signed a treaty, it doesn't mean that they trade a lot. Lots of times, countries sign treaties in an attempt to boost trade, but it doesn't necessarily mean that they trade. So maybe you just picked a bum variable. So you pick another variable, say for example, trade amount in US dollars. Now we're cooking. We have an actual measure of how much trade is going on. So you rerun the OLS. This time you get a beta of -1.12 with a t-value of 3. The coefficient is negative, which is what we should expect. It is an inverse relationship. The more you trade, the less conflict you have. The confidence interval does not include 0. So now you have evidence that the relationship is actually real. Trade does reduce conflict. So now you find yourself in a bit of a pickle. You have two models that are trying to test the same relationship. At a purely conceptual level, these models are identical. They both regress conflict against trade. But in the first model, we find that the evidence doesn't hold. On the second model, we find that the evidence holds. Which model should you pick? Which model is the best model? Simple. Just look at the adjusted R-square value. The first model, where you use number of treaties, produced an adjusted R-square of 0.18, meaning it explains 18% of the variation. The second model produced an adjusted R-square of 0.27. Pick the model with the highest adjusted R-square. It's the second one. In conclusion, you will often find yourself with conflicting results. Some models will give you high betas but low t's. Some models will give you high t's but low betas. Some will accept the null hypothesis, some will reject the null hypothesis. You won't always be clear which model is the best model. Whenever you find yourself in that situation, simply put all of that aside and just pick the model with the highest adjusted R-squared value. So before we conclude this lecture, let me illustrate its use one more time by further building on our example. You suspect that trade is not the only thing driving cooperation. There are other things that are likely to impact cooperation, such as geographical proximity. That is, cooperation is a product of how close one country is to another. Close countries are more likely to cooperate than countries that are farther away. You find an additional data set that contains two new variables. One variable is called proximity, and he measures the distance from one capital city to another capital city. The other variable is called border, and he basically measures the length of shared borders between two countries. Now you have to build new models and use the adjusted R-squared to identify which model you're going to pick. The thing is, if you have identified that there are more elements explaining cooperation, that means that the previous two models that you have built are biased. Why are they biased? Well, because they did not include everything that explains cooperation. They omitted an important explanatory variable, and consequently, they suffer from OVB, omitted variable bias. If they're biased, we must start everything from scratch. In the two previous models that you ran, you chose the trade in dollars model because it was a better model, but now you can't be confident that that is in fact a better model because that could be a biased result. So you have to start from the very beginning. How many models should you build? The short answer is you should build as many models as there are possible variable combinations. Here you have two variables representing trade. Those are the number of treaties and the amount of trade in dollars. And you also have two variables representing geographical proximity. Those are distance from capital to capital and length of shared borders. That gives you a total of 4 possible models. How did I get to 4 models? Well, the first independent variable, that's trade, has 2 versions, and the second independent variable, proximity, also has 2 versions. 2 versions times 2 versions gives you a total of 4. 2 times 2 equals 4. If the first variable had 3 versions and the second variable had 2 versions, you'd get 3 times 2, which is 6 models. If the first and the second variables each had 3 versions, you'd get 3 times 3, which equals 9 models. Don't worry about that though. I wouldn't ever ask you to compute 9 separate models. That would just be too mean. Anyways, here in this case, we're going to end up with 4 possible models. The first model would use the variable number of treaties, and the second variable would be capital city to capital city. Model 2 would also use number of treaties, but now instead of using capital city to capital city, you would use shared length borders. The third model would swap the first variable, trade, and instead of using number of treaties, you would use trade in US dollars. And then the second variable would be capital city to capital city. The fourth and final model would also use trade in US dollars, but then instead of using capital city to capital city, you would use shared borders. In that way, you would walk away with every possible combination of variables. Remember that every single regression that you run must contain these 2 variables, because conceptually you identified these 2 as important explanations of what causes conflict. If you keep them out, meaning if you run OLS without one of these variables, with one of these variables missing, you will be suffering from OVB and your results will be biased. Once you have ran these 4 separate models, the question is, which model should you pick? After all, Now you have 4 separate models that likely contain competing results. Some might have high t's with low coefficients. Others might have high coefficients but low t's. Well, you navigate the situation by simply picking the model that produces the highest adjusted R-square value. Only after you picked a model that you should move on to do the hypothesis tests, that you should move on to evaluate the push and pull of each variable, that you should move on to identify which variables is the most important driver, all of the good stuff that we've learned before. This is all done after you picked the model. So this concludes our illustration of how this measure can help us with our OLS challenges. Before I let you go, I just want to remind you that you can get the adjusted R-square value from the model fit box in the SPSS results. Just rewatch the OLS SPSS tutorial and you will see where to find it. It's pretty straightforward. Alright, have a great one, and I'll see you in our final lecture.